So dynamics is a challenging unit, so I thought we would go through the test together and look at both what the right answers are, but also why they are that way. The first question you all got right, which is great, which is what are you thankful for? So I'm thankful for my awesome students. You guys have been amazing. Um, Thank you for all the hard work that you've been doing in this unit so far. It is really not easy to learn on your own at home, and you guys have been doing a fantastic job, so I'm really proud of you. All right, diving into the physics. So question 2, we've got you standing on horizontal ground. So here's you. And you feel the force of gravity down. You also feel the normal force up. And those happen to be the same size. Gravity is negative 588 newtons and the normal force is positive 588 newtons, but they're in opposite directions. So equal magnitude, opposite directions. When you see equal and opposite, that makes you think of Newton's third law, but that is actually not true. This is not a Newton's third law situation. So Newton's third law is always about forces on different objects, on different free body diagrams. So let's say you have Amy here, and maybe Amy is pushing on Bob. So if Amy applies a force to Bob, that's the force of Amy on Bob, then Amy will feel a force back from Bob. This is the force of Bob on Amy that's the same size. And those two forces are action-reaction pairs. So that is equal to that because of Newton's third law. But notice how those forces are on two different people. The normal force and gravity are both just on you. They're on one person. That means they could not possibly be action-reaction pairs with Newton's third law. Newton's third law is always about one object. Object A pushes on B, so object B must push back on A. So if we actually think about what would be the action-reaction pairs to the normal force and gravity, well, gravity is the force of the Earth pulling down on you. So the action-reaction pair to that would actually be a force of gravity of you pulling up on the Earth. So the action-reaction pair to gravity is you pulling up on the Earth. And the action-reaction pair to the normal force would be on a different object again, right? So the normal force is the ground pushing up on you. So the action-reaction pair to that is you pushing down on the ground. So which is not the same thing as gravity at all. So these guys are not action-reaction pairs. The other way you know they're not action-reaction pairs is that they're actually not always equal. Action-reaction pairs are equal all the time, even if you're accelerating. In this case, the normal force and gravity are equal because you're not accelerating. But let's say that you are accelerating upwards. So let's say you're standing on the ground, but you're jumping, right? You're jumping upwards. In that case, the normal force would be bigger than the force of gravity. They would no longer be equal to each other. They'd still be in opposite directions. Or let's say you were on a hill. Well, in that situation, the normal force would be like this, perpendicular to the hill. Gravity would be straight down. Those aren't even in opposite directions, and they're definitely not equal. So in that situation, you can see that they're clearly not action-reaction pairs, but they're actually never action-reaction pairs. The normal force and gravity are on the same object, so they can't be. So why are they equal? They're equal to each other because of Newton's first law. So Newton's first law is that so here's you. If your acceleration is 0, which it is, you're just standing still, then all the forces on you balance out. And you happen to only feel two forces if you're just standing on the ground, which is gravity and the normal force. So they have to balance each other out, which is why they're equal to each other. So the right answer should be this one here. Because your acceleration is 0, those two forces balance out according to Newton's first law. It's actually not a third law situation at all. All right, question 3. So you're parked in an airplane on a runway, and maybe you've experienced this. The engines turn on and you'll feel like this really strong acceleration forward down the runway. So here's your chair, and here's you sitting in your chair. You're going to accelerate forward really, really fast because the plane is accelerating forward and you're moving with the plane. So you're definitely going to have a forwards acceleration here. Now, what's tricky about this question is that you probably feel like you're moving backwards. You're not moving backwards at all. What's happening is that you have, like, your stomach has some inertia here. So there's your stomach. In fact, all of you does, but I kind of like to focus on your stomach because you can really feel it often in your gut. That's kind of where you experience the feeling of inertia. So your stomach wants to stay at rest. It doesn't want to move. Your inertia is just this tendency of your body to keep doing what it was already doing. It was at rest a moment ago, so it wants to stay there. But then the seat starts pushing into you, right? So the seat is pushing you forwards, applying this really big force forwards. So it actually compresses you a little bit, like you feel like you're being squished back into your seat, but in fact, that's actually just because the seat is pushing forward into you, and that's while your stomach wants to stay at rest, which causes this feeling of compression. So what's actually happening is that your stomach doesn't want to move, but you feel a net force forward, and that causes you to actually accelerate forward. All right, this was a really tricky one, but we actually did do an example in class that was identical to this. It just looked different. So I'll do that one first. So the one we talked about in class just before March break is if you have like a ball on a string, and that ball is going in a circle around and around and around like this, then that ball is going to feel a force, and the force on the ball will always be towards the center of the circle. The net force on that ball has to be towards the center of the circle. Oh, sorry, I made that an E. It should be an F. For force, there we go. There it is, an F. So the net force on the ball has to be towards the center of the circle. Why is that? Well, the ball has some inertia where it wants to keep moving this way. So this is just the ball's inertia. But in order to make the ball start to curve inwards, it needs a force to do that, and that force towards the center of the circle will cause the curve inwards. The other thing you can really see clearly with a ball and a string is, well, there's only one string. Strings can only pull, and so the string must be pulling towards the center of the circle, because it's not possible for a rope to like push a ball outwards. That would be silly to think about that. So clearly the force must be inwards. Here, you actually have the same situation. So you have this really quickly spinning cylinder here. It's spinning around, which means that this person has some inertia and they want to keep traveling this way, but that's just their inertia. Their tendency to keep moving the direction they were already moving. It's not a force, it's just their tendency to keep going in the direction they were going before. In order to cause them to curve inwards, what we need is a force towards the center of the circle, and that's actually just a normal force from the wall. The wall pushes you in towards the center of the circle, and so the wall allows you to make that curve a moment later. So once the person gets over to here, now their inertia is going to be going this way, and they'll still feel a force towards the center of the circle, and that's going to cause them to curve inwards again. And so they keep going around in a circle like that. The other way you can kind of know what's going on here is that the force is from the wall. Walls can't pull, right? If you're up against a wall, it can't sort of like suck you in, unless maybe it has glue on it or something more complicated, but that's not really what's happening here, right? So the wall can't pull you in. So C is what a lot of people said to this question, but that actually isn't true at all. Walls can't pull on you. The wall is actually pushing you towards the center of the circle. The only reason why you feel thrown towards the outside of the circle is because of your inertia causing you to want to go in a straight line. All right. Here's another inertia question. So let's say you have a cat toy with a ball going around in a circle. The one that we talked about in class was quite similar to this, but we talked about it as in the Earth going around the sun. So if here's the sun, and here's the Earth here, and the Earth is going around the sun like this, and then imagine gravity just turned off at this moment here. If gravity just turned off, then what the Earth would do is it would keep doing what it was doing before. And so our inertia is the tendency to do what we were doing a moment before. And inertia doesn't have a memory. It doesn't remember that we were going around in a whole circle. It just remembers that a moment ago, I was going this way. So I'm going to keep going that way. And the Earth would just keep going this way forever. That's what its inertia would do. So it would just keep going in that direction forever if gravity turned off. Same situation is going on here. So this ball is going around the ring like so, around and around and around, and then just at this moment when it's at the top, the walls collapse and the ball can roll freely. So a moment before it was going this way, so the ball's just going to keep going that way in a straight line forever. So that's the idea of Newton's first law. Objects will keep doing what they're already doing if there's no net force on them. They'll just keep going in a straight line if they were moving before. This one was a fast one. So the definition of weight is the force of gravity on a person. So it's not the same as your mass. It's a bit confusing because in sort of colloquial language, we interchange mass and weight as if they're the same thing, but they're not. So weight is the force of gravity. The units, in case you're wondering, would be newtons. So if someone asks you how much do you weigh, you should say your weight in newtons, not kilograms. The mass is measured in kilograms, right? But weight is the force of gravity on you. So that means your weight actually changes if you go to the moon, right? If you were going to a planet where gravity was lower, you would have the same mass. Your mass stays the same. Your number of kilograms you are wouldn't change, but your weight, the force of gravity on you, would change. So that's what weight means. All right, 7 and 8 were tricky. So 7 and 8 were in some of the practice problems that you did before. So there's a truck here pushing on a little car. And we're told initially that they're going at constant speed. So we know that the car is going to feel a force from the truck forward. And then the truck is going to feel a force from the car backwards. And notice that those are on two different objects. And those are going to be action-reaction pairs with Newton's third law. So this is a Newton's third law situation. So because they're action-reaction pairs, that means the force that the truck exerts on the car must be equal to the force that the car exerts backwards on the truck. So those two have to be equal to each other. Question 8 seems like it's a lot harder. Like, oh, what if this whole thing is accelerating now forward? But the reality is that Newton's third law always applies. Even if objects are different masses, even if objects are accelerating. So that means that the force that the car exerts back on the truck is still just as big as the force that the truck exerted on the car in the first place, even when you're accelerating. Now, what you might be thinking is, wait, how could you accelerate if these two forces are equal? Don't they like cancel each other out? They won't cancel each other out because they're on different objects. So this car just feels the force from the truck forward, right? It's not going to feel a whole lot of backwards forces, so it can still accelerate forward. This force and this force, we're not going to ever add them together and make them cancel out because they're on two different free body diagrams. They're on two different objects. All right, in question 9, this is one that you did in the notes. So you've got a rocket initially moving this way, and then the engines turn on and you feel this constant acceleration up. So what's going to happen is the rocket has inertia, and the inertia is to the right. So it wants to like keep moving right. So this is sort of the path that the rocket wants to keep taking. But you're adding this acceleration upwards, so that's adding some velocities upwards, which means that the rocket has to keep moving forward. But as time goes on, the velocities in the upwards direction get bigger and bigger. So you have a little velocity, and then it gets bigger, and then bigger, and then bigger. And what that looks like is a curve. So what the rocket ship will actually do is this nice, gentle curve like that. And that is it for the concept questions. So then we dove into the problem solving stuff. The first one was just to draw a free body diagram. If you have a skier on a hill, so you draw the hill and the 30-degree angle is down here. It's with the horizontal. We can draw our little skier guy here. The forces he would feel would be gravity. Gravity should be straight down. He'd feel a normal force. The normal force is always perpendicular to the surface, so that should be a 90-degree angle in there. And he's skiing down this hill. That's his skis there, right? So the friction force will oppose the slide. He's sliding down, so friction must be back like this. And it's going to be an FFK because he's sliding. So sliding is a kinetic friction. Static friction is not sliding, any sort of not sliding situation. The best coordinate system for something on a hill is going to be to make your y-axis perpendicular to the hill and the x-axis parallel to the hill. And that's actually all you had to do for this question. Just to show you one more thing though, often in questions like this, you have to sort of solve more stuff, right? So if you were going further in solving this, The next thing you need to do is split gravity into components. So what you would be doing is you're splitting any force that's not parallel to y and x into components. Notice that the normal force, it's parallel to y, so it's already good. The friction force is parallel to x, so it's good. The only one that's a problem is gravity. It's not parallel to y or x, so you have to split it into components, and you do that like this. This here would be FGY. What you do is you go parallel to y, which is exactly 90 degrees to the hill. That's the y component. And then you have to make a right angle turn here. And you want to go nicely parallel to the hill. So that's FGX. Those should be at right angles to each other. And then you can solve for FGY and FGX using some SOHCAHTOA. If this is 30 degrees in here, that's going to be 30 degrees up there, and you can kind of take it from there. But that wasn't required for the problem. You just had to draw your three forces. Right, here's one with a little bit more math. So here, what we want to do is find all the x and y components of every force and then just add them all up and then get the net force altogether. So it's good to make a chart. X and y stuff, that can be helpful. So F1, we can split it into two components. You could split your components kind of like this. A good coordinate system here would just be the regular one. So y is positive this way, x is positive this way. So this would be F1x here, and this is F1y. So F1x is going to be negative. Notice that it's going backwards here. And it's going to be negative F1 cos of 25. Cos because it's close to the 25-degree angle. F1 is 78 newtons, so we're going to do 78 cos 25, which is negative 70.692 newtons. And then there's F1y over here. F1y will be positive because you can see it's up, and it'll be F1 sine of 25. So calculating that, that'd be 78 sine 25, which is 32.964 newtons. Our next one, F2, has components that are going down here. So that's F2y. And a component forward, that's F2x. So F2x, notice this one is opposite the 30-degree angle, so it's going to be sine. So it'll be F2 sine 30 degrees, and it's positive because it's forward there. So F2 is 57, so 57 sine 30 is 28.5 newtons. And then we have F2y. F2y is going to be negative, see how it's going down there, and it's going to be negative F2 cos 30 because it's close to the angle and cos is close. So F2y is going to be negative 57 cos of 30, which is negative 49.363 newtons. And our last one, F3, in the x direction, F3 is actually 100% in the x direction. You can see it's in the negative x direction, so it's going to be negative 43 newtons. And there's no component of F3 in the y direction, so that would just be 0. Then what we do is we add everything up in x, and we add everything up in y. So you're just going to add up all of those numbers. So you'll add up F1x here, F2x, and F3x, and that gives me some negative 70.692 plus 28.5 plus negative 43 is negative 85.192 newtons. And then in the y direction, you're going to want to add up F1y and F2y. F3y is 0, so that one's not to worry about. 32.964 plus negative 49.363. And that gives you negative 16.399 newtons. All right, now I need to draw those two forces and combine them into one triangle. So I like to draw Fx first. Notice that it's negative, so that means it's going to be going backwards. So that right there is my net force in the x direction. And then from the tip of that force, so right from there, you want to draw Fy, and it's -2, so it's going to be going down. So that's Fy there. And the force that I'm looking for is the force from the beginning, the start here, right to the end there. That is the net force. So to calculate the net force, I actually can just use Pythagoras' theorem. So I'll do the square root of the -85.192 squared. The negative side actually doesn't matter, right, because it's all getting squared. And then the -16.39, is that a 399 squared there. So we add those together. So square that, square the other one, add them together, square root the whole thing, and you get a net force of 86.7. Now actually, let's just check our sig figs here. It looks like we only have 2, so let's round that off. 87 newtons. So that's my net force here, but I'm actually not done, right? Because I need to calculate an angle. A good one to calculate is the one in the base of your triangle. So this one, not this one. It's better to calculate the one that's at the beginning of the arrow, not at the tip of the arrow. That angle, tan of theta, is going to be the opposite net force in the y direction divided by the adjacent net force in the x direction. So theta will be the inverse tan of that y force, which is the 16.399, divided by the net x, 85.192. So let's do the 16.399 divided by 85.192. Inverse tan that, and you should get 11 degrees. So how do we write that using your northeast, southwest sort of thing? Well, that would be west. So first sort of going west and then peeling away to the south. So I'd say west 11 degrees south is how I'd write that angle down. And that is my answer for the net force there. All right, the very last one. So we have Bob pulling on a couch here, and he's pulling the couch across a horizontal ground at constant speed, and he applies a tension force of 200 newtons at an angle of 23 degrees above the horizontal and forward. So the first thing you need is definitely a Freebody diagram. So he's got a tension force that he's applying here. I'll just draw it right on the picture itself because that's easier. So then Ft, there's going to be a normal force. That's why the couch doesn't fall through the ground. And there's going to be a gravity force. And of course, there'll also be a friction force backwards, and it's sliding, so it's going to be an FFK. We need a coordinate system, so let's make y positive up and x positive forward. We usually make our coordinate system just parallel to the direction that the object's sliding or moving, if it is moving, or just parallel to the ground is a good idea if it's not moving. All right, then we need to split up our tension force into its components. So tension force would have an Ftx here and an Fty there. The next thing I'll probably want to do is just calculate the force of gravity. Because gravity is down and I've made y positive up, it'll be negative, and it'll be negative m times g. So that's negative, the mass of my couch is 40 kilograms. G is 9.8. So toss that into your calculator. The force of gravity should be negative 392 newtons, just straight down there. I can calculate the tension in the y direction and the tension in the x direction. So the tension in the y direction is going to be Ft times sine of 23, and that's because it's opposite the 23-degree angle. So the tension force was 200 newtons, so 200 sine 23 is 78.146 newtons. It's positive because that's up. Ftx is going to be Ft cos 23. So Ftx will be the 200 cos 23, which is 184.101 newtons there. And it's also positive because it's forwards. There's no sort of formula I can use to calculate Fn or FFK actually at this point, although you will learn a formula for FFK soon, but we don't have one yet. So our only strategy next is to sum the forces. So summing the forces is a key thing that you will sort of always do in these kinds of questions. Let's sum them up in the y direction first. So in the y direction, there's actually three forces going on here. There's a normal force, there's a gravity force, and there's the y component of tension, Fty. We also know that this couch is not even moving in the y direction, so it's definitely not accelerating. So that means the net force in the y direction is 0. So you can say that 0 is equal to that Fn plus the Fg plus Fty. And now I actually know Fg and Fty here, so all I have to do to solve for Fn is move these two guys to the other side, so they just become negative. Negative Fg, negative Fty. So that means I'll have negative 392 minus the 78.146, like that. Notice the negative makes a positive, right? So positive 392 minus 78.146, and we get a normal force of 314 newtons. I'm just rounding off to sig figs now because I know that's I'm basically done at that point with that force, right? So that will be the normal force right there. Just a sanity check to make sure that makes sense. The normal force is a little bit less than gravity, right? It doesn't quite balance out gravity. That should make sense here because basically this tension force is helping you a little bit, right? This tension force is helping out the normal force. You've got two up direction forces that together have to balance one down force, so the normal force doesn't have to be quite as big as it otherwise would. So that kind of makes sense. Next, we do the same thing in the x direction. So sum up your forces in x. You've got FFK and FTX, and that's actually it. Same idea as before, acceleration in x is 0, so that means the net force in x is 0. So I can say 0 is equal to FFK plus FTX, and then just move the FTX to the other side, and you'll get FFK on its own. So the friction force is negative of the x component of the tension force, which makes sense. So FFK is going to be negative. The x component of the tension force was 184, so negative 184 newtons. And that is my friction force there. We've got gravity is here, and the tension force we were given in the problem is 200 newtons. And so that is all the forces on the couch.